Yeah, you can start.
Good morning, respected teachers, and to one and all present. My name is Tithi Moktan. I'm from the fifth semester, and the topic for my presentation today is graphene. What is graphene? It is a material which has been there all the time, and we've been playing with it since we started writing. The figure that you see here is graphite, which is found in pencil leads. They are basically composed of layers of carbon atoms, and if we could take just one layer of graphite, that is what we call graphene. So, graphene can be described as a single layer of graphite that is just one atom thick. This means that every time we are writing, we are leaving traces of graphene sheets on the paper. We can also call it an allotrope of carbon that are densely packed in a honeycomb or hexagonal lattice. It is the first 2D material ever discovered and the basic building block of all graphitic materials. It is the lightest, strongest, and the most conductive material ever known to man, and due to this, graphene is also known as the wonder material of the 21st century. Moving on to the structure, each carbon atom is hybridized in graphene and forms 3 sigma and 1 delocalized pi bond. Each atom is bound to its 3 nearest neighbors, and the bond length is equal to 0.142 nanometer, which is less than that in diamond. As said earlier, graphene is a basic building block for all graphitic material and can form other allotropes. It can be wrapped up into 0D fullerenes, rolled into 1D nanotubes, and also stacked into 3D graphite, all of which has its own unique properties. Moving on to the discovery. Although scientists knew one atom thick graphene existed, no one had worked out how to extract it from graphite. That was until it was isolated in 2004 by 2 researchers at the University of Manchester, Professor Andrew Game and Professor Kostya Noslev. In 2010, they were awarded the Nobel Prize for groundbreaking experiments regarding the two-dimensional material graphene. They used the Scotch tape method, in which the Scotch tape was pressed onto the graphite and was peeled away when some layers stuck on the surface. The layers on graphene was thinned using the tape and was placed on a silicon substrate. The unit cell of a graphene's lattice consists of 2 different types of sets, which we call A sites and B sites. A1 and A2 are the basis vector, and using B1 and B2 as the reciprocal lattice vectors, a corresponding brilliant zone is drawn. The first brilliant zone is a hexagon and sigma is its center point. This is the solution of the energy bands of graphene, and the Dirac points are the transition between the valence band and the conduction band. The 6 Dirac bands can be divided into 2 non-equivalent sets of 3 points, that is represented by K and K dash, represented by the black and white dots as you can see in the figure. The 2 bands, they touch each other at the zone corners where there is no band gap. Comparing the band structure of semiconductor and graphene, we can see that in an insulator or semiconductor, an electron can break free only if it gets enough energy to jump the band gap. But in graphene, the gap is infinitesimal, so the graphene can move easily and very fast. Thus, the graphene sheet displays a semi-metallic, also known as zero-gap semiconductor character. Moving on to the mechanical properties, it has inherent strength. Due to the strength of its 0.142 nanometer long carbon bonds with an ultimate tensile strength of 130 gigapascals, according to the Nobel Prize paper, a hammock of graphene could hold a cat of 4 kg weight while weighing the same as one of its whiskers. Not only is graphene extraordinarily strong, but it is also very light at 0.77 milligrams per square meter. Graphene also has elastic properties and has a Young's modulus of 0.5 tetrapascal. It is so impermeable that even the smallest atom, that is helium, cannot pass through monolayer graphene. It also has some of unique optical properties. Even though it is one atom thick, graphene is still visible to the naked eye, as you can see in the figure. Due to its unique electronic properties, it absorbs 2.3% of light that passes through it. Moving on to the applications. Uh, it has various applications like ultrafiltration. Another standard property of graphene is that while it allows water to pass through it, it is completely impervious to liquids and gases. This means that graphene could be used as an ultrafiltration medium to act as a barrier between two substances. Offering very low levels of light absorption at around 2.7% while also offering high electron mobility means that graphene can also be used as an alternative to silicon. Graphene is strong, stiff, and very light. Currently, aerospace engineers are incorporating carbon fiber into the production of aircraft as it is also very strong and light. However, graphene is much stronger while being so much lighter. Ultimately, it is expected that graphene is utilized to create a material that can replace steel in the structure of aircraft, improving fuel efficiency, range, and reducing weight. It can also be used in optical electronics. It would work very well in optoelectronics applications such as LCD touch screens for smartphones, tablet and desktop computers and televisions. It can also be used in biological engineering, with graphene offering a large surface area, high electrical conductivity, thinness and strength. It would make a good candidate for the development of fast and efficient bioelectric sensory devices with the ability to monitor such things as glucose levels, hemoglobin levels, cholesterol, and even DNA sequencing. These are some of the references that I've used to make the presentation. And this is the end of the presentation. Thank you.
Thank you, Tithi. Do any of the students have questions?
Sir, in practical, can you understand it is actually one layer? It has actually one layer because it's very difficult to read, not read, to see this that it has a one layer atomic system.
Yes, actually, it is one atom thick, and it has been like they have actually obtained it using the Scotch Dept method. The first method they used was Scotch Dept method. The Nobel laureates, yes, they did it using the Scotch Dept method, where they were able to find this. They were able to isolate this one layer graphene.
Okay.
Any other questions? All right, Siddhartha ma'am, you have questions for Tithi?
Sir, you can ask.
Okay. Digvijay sir, any questions?
So Tithi, you talked about Brillouin zone. So what is a Brillouin zone?
We draw. It is like basically a Wigner cell, which we say that we draw. We join the one lattice point to its nearest neighbors, and we draw a perpendicular, and the area which is enclosed inside it is the first Brillouin zone, and again we continue the process to receive other Brillouin zones.
In which space do you draw a Brillouin zone?
I think it's momentum space, sir.
Okay. Okay. So you also talked about band gap.
Yes, sir.
Do you know about indirect band gap?
No, sir, I had no idea, sir. I didn't read about that.
Okay. Okay. Yeah, that's all for me, sir.
Okay, Tithi. So I actually quite like the formatting of your presentation. the background, the font that you use. Actually, can you go to your second slide?
Yes. This one, sir?
Yeah, this is good. Yeah, show that one.
No, what's wrong with this?
Why don't you try pressing that display button on? Yeah, from current slide. There you go. Yeah. So, like, this is just an example slide, but this is quite nice. Like, there's a nice a medium colored background. It is not distracting. The font is large and clearly readable. Your diagrams are nice. Now I can see there's a slight there's some upside down labeling at the bottom, but that's fine. We're going to ignore it for now. So I quite like the construction of your presentation. The big issue that I had is your speed. Your presentation was only about 10 minutes. And I think you could have extended it the exact same thing to 15 minutes by just talking a little bit more slowly. Because you kind of blazed through all the discussion about the band gap and the Brillouin zones, right? So as you go forward, you are presenting different graphs and different ideas, and you sort of rushed through it. And for some of the graphs and things, people, like a lot of people would actually want to sit and kind of absorb the graph, take a little bit of time to absorb the graph and the diagrams. So your pace was a little bit too quick. You will want to cut it down a little bit when you present the next time if you ever have to make a presentation. Okay. But aside from that, it was my main problem was with your pacing, like how quick you were going. Aside from that, I think the presentation was quite good. I quite like the construction. It's nice and simple, nothing ostentatious, but fairly it's competently made. Okay. Regarding questions, can you go forward to the slide for fullerenes and things like that? There was a slide where you showing the different dimensional graphene. Yeah, this one. Can you talk about some of the uses of fullerenes and nanotubes and graphite? Did you read through any of those things?
No, sir, I didn't go through it, but I know that carbon nanotubes, they can be, they also have good conductivity, and they can be used to make like wires. But I didn't go into fullerenes, sir.
Okay. Yeah, no. Excuse me. Can you go forward a few more slides to the one where you were talking about the, I think the optical, like how it is transparent, mostly transparent to light. Yeah.
This one.
This is the one where you talk about the helium atom.
Oh no, sir, this was in mechanical
Oh yeah, this
properties.
one, mechanical properties. Is the smallest atom helium? What's the smallest atom?
Sorry, sir, I didn't get your question.
What is the smallest atom? No, go back. Okay. So the last line says, it is so impermeable that even the smallest atom, and in brackets I've written helium, cannot pass through a monolayer. Is the smallest atom, what is the smallest atom?
Hydrogen.
Okay. Do you know why they didn't use hydrogen? Why do you use helium?
It's a gas, sir. Helium is a gas. So,
So is hydrogen. What kind of gas is helium? Helium,
gas,
argon, neon.
so it's an inert gas, sir.
Yeah, it doesn't. It won't have any sort of chemical interaction with the carbon. Hydrogen, on the other hand, likes having chemical interactions with carbon. That's probably why they didn't make it there. That's probably why they didn't test it with hydrogen. Would I be wrong, Big sir? I think this is more area.
Yes, sir. Yes.
Okay. Yeah, but aside from that, Tithi, aside from the pacing, like the fact that you are very quick, I quite like the presentation. That's quite good. Okay. Sujata ma'am, any questions?
Yes, sir. Okay, Tithi. So, you have told about honeycomb lattice structure. So can you give me brief description about honeycomb lattice structure?
Yes, ma'am. It has 6 sides, mm, and the atoms are present on the vertex, and
And
it is a non-Bravais lattice. I don't know.
okay, so here your juniors are here. So I think you have read your CC12. Okay, so, in the first chapter of CC12. So can you tell me what is lattice at first? What is lattice?
It is just imaginary points, ma'am. Imaginary points which is drawn.
For what?
It in combination with the atoms, it gives the crystal structure, ma'am.
Okay, okay. Then tell me then what is primitive unit cell?
In which the effective number of atoms per unit cell is 1.
And what is effective number of atoms?
It means the atoms which is inside the unit cell, ma'am.
Okay. So what you can do, it is just a suggestion. Like you have juniors, and you know your juniors will also be there, and they don't know anything about lattice structure, unit cell, primitive unit cell. Okay, so you could make one slide. In one slide, what you will show that what is lattice, just the structure. Okay, in there will be picture you can just describe. So at first some lattice structure, then in general rectangular, that kind of. After that this honeycomb type, this is special type of lattice structure. Okay, so
Yeah.
this is just one suggestion.
Yes, ma'am. Okay.
Otherwise, like for juniors, it is very difficult to understand what is going on. Okay, basically in graphene the most important thing is its structure. And like Shonajit asked about one layer. Okay, and do you know about the graphene means is it harmful to human body?
Some research shows that it is toxic, ma'am. And again, I did some papers where it says that it is completely safe. So I couldn't come to a conclusion, ma'am.
Okay, okay then, this much.
Yes, ma'am. Thank
Okay,
you,
so
ma'am.
over to you.
Okay, I'm going to open the floor to any last minute questions by any of the students. If they have any more questions. Okay, I don't see anybody unmuting. So thank you so much, Tithi. Thank you for your
Thank you, sir.
presentation.
Thank you, ma'am.
Yeah, you can stop your screen sharing.